Hey everyone, and welcome to This Explainer. If you're a focused learner looking to seriously elevate your verification game, well, you're in exactly the right place. Today, our goal is to completely demystify Universal Verification Methodology, or UVM communication. We're going to break down how data actually moves in a modern test bench, and honestly, the source material reveals a system that is just surprisingly elegant once you get the hang of it.
But first, let me ask you something. Are you still relying on those awkward pin sequencer workarounds? Still wiggling low-level RTL pins just to get your components to talk to each other? Okay, let's dive into this, because today we are officially escaping the dark ages of pin wiggling and messy configuration databases. By the end of this explainer, you'll see exactly how to make your test benches truly modular and reusable.
Here's our roadmap to building out this factory assembly line. 1. Setting the UVM foundation. 2. Intro to transaction-level modeling. 3. Put, get, and peek. 4. Ports, exports, and imps. And finally, 5. Broadcasting with analysis FIFOs.
All right, Section 1. Setting the UVM foundation, phases and resources.
So before we can start moving our data, our goods, around the factory, we absolutely must understand when and how our factory components are actually built and configured. The crucial point here is understanding the UVM timeline. You know, in SystemVerilog, keeping everything synchronized is pretty tough, right? So UVM uses phases. The build phase is where components are created, top-down. But the magic really happens in the connect phase and the run phase. The connect phase is non-time consuming, meaning it executes in zero simulation time. This bottom-up phase is where we wire together all our communication ports. Later, the actual data moves during the run phase. That's a time-consuming phase where all components execute in parallel using threads, kind of like a fork join. Bottom line, you literally have to wire the factory before you turn on the power. And speaking of setting up the factory, how are you sharing your configuration data? For years, over 90% of engineers have relied on the UVM_config_db. But as verification experts point out, that was kind of just a transitional API. See, UVM config_db requires a strict component context and string path. But by swapping to UVM_resource_db, you use simple string scoping and pseudoscopes. This is a brilliant little switch because it means you can access configurations from sequences without ever needing that dreaded p-sequencer workaround again. It completely detaches configuration from the component hierarchy, a real game changer for sure.
Okay, moving on to Section 2, Intro to Transaction Leveling Modeling, the factory floor. Now that our components are built and properly configured without all those messy workarounds, we can move from static setup to dynamic data flow. Transaction Level Modeling, or TLM for short, is basically a message passing system. Instead of driving discrete bits and wires, which, let's face it, is incredibly slow and a huge headache to maintain, TLM exchanges information as objects. We call these transactions. Think of transactions as the physical products moving on the conveyor belts of our UVM factory. By abstracting away those low-level RTL details, your simulation runs so much faster, and your components become highly reusable across entirely different projects.
So on this factory floor, we essentially have two main roles. The producer is the component that generates a transaction, and the consumer is the component that receives and consumes that transaction. Pretty straightforward, right? But how do they actually hand off the goods?
That brings us to Section 3, Put, Get, and Peek, Moving the Goods.
Now, what's really interesting about this slide is looking at the UML diagram for the unidirectional put interface. The square box typically represents a port on the producer. Here, you can see that the producer initiates the action. It has a transaction ready, and it actively puts it into the consumer. And successful completion of a put operation absolutely guarantees that the transaction was delivered successfully to the target.
Let's break down the actual code behavior behind these three main operations. With a put, the producer pushes the data. If it's a blocking put, imagine the producer standing there with its hand out, completely frozen, waiting until the consumer is 100% finished processing the transaction. A get is the exact reverse. The consumer asks the producer for a data value. And a peek? Well, it's kind of like a get, but it just copies the data without actually removing it from the producer. Successive peeks will return the exact same object. Oh, and remember, in SystemVerilog, blocking methods are implemented as tasks because they actually consume simulation time, while non-blocking methods are implemented as functions because they execute instantly.
Let's keep it moving. Section 4. Ports, exports, and imps, the wiring.
So we know the actions, right? Put, get, and peek. But how do we physically connect a producer to a consumer? This visual brilliantly illustrates the physical wiring of our UVM factory. You can't just throw a transaction into the void, you need a channel. In TLM, connections are made between ports, exports, and IMPs. A port requires an interface, but the port itself doesn't contain the actual code for what to do with the transaction. It just defines the API. The IMP, or implementation, is what actually contains the code for the put, get, or peek method. And the export? It just sits right in the middle to forward the implementation across component boundaries.
Let's move to and see how this builds chronologically when a transaction crosses a component boundary. Step 1, the port in the initiator component makes the call, say a put request. Step 2, that request hits an export. The export acts like a pass-through router, promoting the interface implementation from a child component up to the parent level. And step 3, the request finally reaches the IMP. The IMP is an object that provides the actual interface through delegation. It's the end of the line where the actual SystemVerilog code for the method executes. The cool part? Neither the initiator nor the target needs to know anything about each other. They just rely on the standard wiring.
Almost at the finish line. Section 5. Broadcasting with Analysis FIFOs. One-to-many.
But what happens when you don't just have one producer and one consumer? What if your components need to operate independently? Or one transaction needs to be evaluated by a scoreboard, a coverage collector, and a monitor all at the exact same time? Well, here we're comparing two incredibly useful structures, the standard UVM TLM FIFO on the left and the UVM TLM Analysis FIFO on the right. A standard TLM FIFO buffers transactions between two independent processes. The producer puts a transaction in, and the consumer independently gets it out whenever it's ready. But an analysis FIFO is a specific variant with an unbounded size and a very specific write interface indicated by the analysis_export. It's designed specifically for the analysis port.
So the crucial takeaway regarding analysis ports is that they are specialized for one-to-many non-blocking broadcasts. They use a single, specific void function called write. Because write is a function, it executes instantly in 0 simulation time. This means a monitor can broadcast a transaction to 5 different subscribers, and its execution thread will literally never block, no matter how long the subscribers take to process the data. But, and here is a major warning, the port passes a pointer to the exact same transaction object to every single subscriber. If you're a subscriber receiving this broadcast, you absolutely must make a local copy of the transaction before operating on it. If you don't, you'll corrupt the data for every other component that received that pointer. No exceptions.
Mastering TLM flow, from understanding simple put and get methods, to wiring up ports and IMPs, to broadcasting safely with zero-time analysis ports, completely rescues you from the nightmare of low-level routing. It empowers you to build modular, highly reusable verification IPs. So, I'll leave you at this final thought. Now that your components are truly decoupled, what bottlenecks will you eliminate in your next test bench? Thanks for joining me for this explainer.